in. Who are we looking at, Chris?
Okay. So Rhino,
Yes, Chris.
it's monumental effort you've put in over here.
Yes,
Huge improvement since we first started sketching things out with bits of cardboard and the odd piece of chipboard. Eh?
yes, it got much bigger and stronger than anticipated and heavier.
Well, that means it's stable. If you're going to put a 24-inch on you, you don't want it to just fall over, do you?
Yeah, no, it will be stronger than my shoulders if I would push a mirror, that's for sure.
That's why it's here. Okay,
Yeah.
so on the top here, we've got the electronic speed control, one for each axis. The drive for the table
Yes,
and the drive for the arm.
that's right.
So this can lift out of the way, and because you drive them independently, you can just use the table by itself, or you can use the two together.
Yes, correct.
Excellent.
Here on this part here is a drive, underneath the drive with the gears for the turntable. And it's got 4 pulleys here, 2 pulleys there, giving 8 gears. In addition, here are the pulleys at the bottom, and here is a 6-pole motor, which we can run with a frequency regulator and change the speed. Because it goes slow, it's got a forced fan which runs continuously on top here. So we can run it from 50 Hertz down to maybe 10 Hertz or even lower. From 20 Hertz down it will lose a little bit power, so we don't know how much we're going to lose. That's why I put the gears in, you know, it's like a motor car. The speed control is like your petrol, but you still need gears. You know, otherwise you drive in one gear all the way, you know. And if you only do one size of mirror, then you can work out your speed beforehand. But we wanted to, I mean, that was your idea, to get a versatile machine.
Of course, because you don't want to use it just once. It's a lot of effort to make a machine to just make one mirror. All right. So what we have is this motor drives through the pulleys to this spindle. This spindle is now encased with rubber, which is a bit squishy, and this will then run on the inside of the rim of the table. And the edge of the table sits on these and is constrained therefore to operate only in one plane. As this spindle biases it outwards, it pull in against these pulleys here, so it can't move laterally.
Yes.
Okay, so let's do a bit of an assembly then. If we move that into a neutral position where it's not engaging anything.
Okay.
The next thing is we don't want the motor to get full of water. So
Right.
what are we going to do about that?
Okay, so we've got to put a water tray or trough in there, which collects the water and the sludge and all that nasty things. It's loose, so you can move it out of the way.
And we can choose where we want the drain to go.
There's a 1-inch drain here, and we can put something under when we want. So it fits just to clear the bearings. All right, so now I'm going to put the turntable on.
Right, let's
This
the
is the
underside of the
top of the turntable. That's the bottom part.
Okay, so this is a strong stainless steel band you've got here that's been machined on the inside to be perfectly circular and perfectly flat on this edge. So this edge is running vertically onto these bearings, and that's supporting the table. So this would take an enormous load. I mean, you could put a truck on top of here without any trouble.
You can sit on it. Yeah.
Okay, and then these rollers will run on the inside, and the rubber roller will then provide the drive through friction.
Yes, by tensioning. Yes.
So if for some reason things seize up, then it can still just slip on here.
Yeah, that's the weakest link now.
But that's the safety mechanism.
Right.
Okay, so let's put the table
put the
on.
table on.
Oh, I see there's a skirt on it as well over here, a little thin skirt, which will overlap here so that any splashes or dribbles will go into the trough instead of into the motor.
Right, because you have to wash the mirror every now and then you can just leave it on the turntable while you do it.
Okay.
All right, there you see, quite easy. Put it on.
Barely drives smooth. One finger. This is quite heavy.
That
So
is
what's
heavy.
inside here? Because it looks like it's quite a strong structure between the
Yeah.
metal parts.
Yeah, it's a double layer of marine ply glued together with a 0.6 millimeter stainless steel
Skin on both sides.
on both sides to stop the flex. And then of course that ring which is underneath, which is quite heavy, and then the brackets on it.
Excellent.
And this is a 3 millimeter ring on the outside, so that's also fits to the weight. You know?
Very rigid.
Yeah. So we can demonstrate maybe by starting up the.
Okay, but we need to engage the...
I have to tension that rubber.
Okay. All right. So basically, the swing arm that the drive assembly is on is being biased, and there's a chain which you can pull on, which has got a spring. If you look underneath here, perhaps. So the spring is just now tensioning the wheel. You can see the arm can move away, or it can engage, and you just notch it like that, or the next one if you want more tension on it. Okay. So now you can't move this by hand, because of the gearing on the motors.
All right, shall we start the turntable first
Yes, let's see.
before we put the arm on? So I've got the variable speed here. It only runs on one gear now, of course, and there are 8 gears. So we can start this up.
Chris, you got loose fan belts under there.
Yes, the thing there is that we have several pulleys, and they have different diameters, and we couldn't arrange it so that one belt would work on all the gear sets. And therefore, there's some spare belts for the other gear sets, basically, the other ratios.
Yeah, I just left the belts there. It's then if you want to change, it's easier. Otherwise, you must loosen the bearings and put it on, which you also can do. It takes 10 minutes.
But you don't want to have to take off your mirror and everything. You know, I can just change the speed. That's nice.
So I can run it a bit faster now on that gear. Alright, that's a table. So now, if we have a look now at the eccentric side, and if we can have a closer look, what we've got there, we've got a motor, and we've got a deduction gearbox next to it, which drives this shaft. And that output from the gearbox is 20 RPM. And then we've got also here, we only got one pulley here, 2 there, 3 there, sorry. So it's a 3-speed. We can adjust there. That's like the eccentric moves. Okay, 3 gears. And then we've got there, of course, also the variable speed.
Okay, so the output shaft of this thing comes to a crank arm here with a slot in it. So you can adjust the position of this in the slot, and that then is changing the radius from the drive shaft, which will in turn change the sweep length of the stroke. And this coupling allows us to put things a little bit offset if we need to work off on one side of the mirror.
And that slot there, we put your hand in.
And this also allows you to move the mirror in and out, or the tool in and out, depending which one's on top. Okay? So.
Alright, I put the wood on just for protection, otherwise we stretch.
So this is simulating the mirror, basically, which for a mirror of this size you'd be working face up.
Right, I put a small mirror glued under here.
So this is the tool then for our big mirror. And on the top of this is a bearing which can requires a bit of force, right? So it's on there. Now you can see that this articulates because it's got spherical bearing there. Right. So the reason for this, if we just put it down, is that if you've got a big curve, then the tool needs to follow the curve, and it can't stay in a plane. It has to be able to move from the one side to the other and rock as it goes. And it needs to be able to rotate as well, so that it will work on all the diameters as it operates. So at the moment, this is not in its normal plane, because as your stack of glass changes thickness, you might have to move this up or down, and so this shaft can actually be raised, and that shaft can be raised so that the arm will be lying in a horizontal plane. But for the purposes of the demonstration, I think that's fine. Okay, so let's see what it does.
Again, we can control it, the motor speed, with the frequency controller. And with this one here, we can just now change the eccentric a bit. We want a bigger swing. Shall I do that?
Yes, let's do that.
Let's turn it down quickly.
Should we do the turntable at the same time?
Yes, we'll do that at the moment.
Okay. That's an improvement still, I must say.
Yes, it's called the demonstration.
Yeah. Okay, just move it there a bit. I think that helps me. Okay.
So that will have a nice, comfortable knob on it then.
Yeah, and that's actually inside which I have to make improvement. Okay, let's see the bigger swing now.
That's pretty cool. Right, let's have the whole ensemble working. Now you can see how just through basic friction the tool is rotating because of the differing radii that it's encountering as it moves in and out across the bottom element. Now if you come closer to it, you will see that I previously put my pen in place of the tool and it's carved out this spirograph kind of pattern here. You can see it's all beautifully regular, but it never goes over exactly the same place twice. And by varying the relative speeds of the tool and mirror, in other words a turntable and a crank, you can get it to behave differently. As I say, the proof of the pudding is in the eating. We're getting close to being able to actually try it on a real piece of glass and see what it does.
And this is a combination of who and who?
Okay, so this is a lot of people's input actually. The basic principle of the single swing arm like this and the horizontal table is the Elgin style of machine. If you were to articulate this so that it could move like that as well as sweeping, then that would be like the Zeiss machine. The other things like the Draper and the Hindle machines, which are rather more complicated. But you can see that determining what pattern it's tracing, what path it's tracing is already complicated enough. And as you add in more elements that you can adjust, it becomes almost impossible to understand what the machine is actually doing. So the Elgin has proved to be like the benchmark, and in industry it is it's widely deployed and gets excellent results. So we thought we will start with the Elgin machine. And then there was all the brainstorming. In this, the big innovation is the table support and mechanism to drive it. Normally, the machine would have a vertical column with huge bearings, and then it would be cantilevered over, and so you need a huge flange so that it is nice and stiff and rigid. And even then, to get it squared on is difficult, and you end up with a thing wobbling as it rotates. And we chose to get rid of all of those problems in one shot, simply by this support mechanism of the three bearings standing vertically that the rim is resting on, and this is so strong you literally could put a truck on the top and it wouldn't jam. Right? We feel that the friction arrangement is going to work well, and well, I did all the big work on making it happen, and the rest of us gave input.
Yeah, two things here. The first one was that it had to be less than 600 millimeter wide, so we can fit it through a normal door to get it into a house or wherever that we want to work with.
The second is that the height has to be low enough that it's
To
not
fit
going
in
to
here.
stay
So these are two constraints.
So,
So this is wider, but we can take it off, of course.
so what we've ended up with is a machine that can take a 600 millimeter mirror, 24-inch mirror, which is quite large, and yet we small narrow parkwood corner get through a door. And that's basically it. Main.
Now that's not too difficult, I think.
Do we want to say that on tape?